Okay, good afternoon all. Welcome back again to the one more interesting seminar today. We have today Lucas with us. He's a PhD student at the Federal University of Santa Catarina in Brazil. He's currently undertaking an overseas exchange program at University of Warwick under the supervision of Ed Bromley, which is a well-known personality in liner designs and all this stuff. So Lucas has more than 7 to 8 years of acoustic liner testing experience in the grazing flow and the state-of-art facility. Currently, he's working on the effects of shared flow on the impedance reduction techniques, and he's co-supervising. I know you're co-supervising many of MSc students, and I can see very interesting papers in the last year AAA. So over to you, Lucas.
So thank you very much, Deepak. Thanks for the introduction. And first of all, thank you for the invitation to come here to this day. Thank you for all of you that joined us either here in person or there are some people online as well. So just one quick question so I can feel a little bit the audience. Who here is a little bit, at least has a little idea of acoustics? I think everyone. So, okay, maybe some parts of my presentation is going to be a little bit too boring for you guys, but I apologize in advance for that. But it's because I prepared this presentation with, maybe with a little bit more of general audience in mind. So as Deepak mentioned, I am a PhD student back in Brazil, the Federal University of Santa Catarina, where we have this little bit more longer procedure. So that's why I seem old and I'm still a PhD student. That's because in Brazil, like 5 years undergrad, then 2 years of master's, then 4 years of PhD. So like I'm already 27 years old. Please don't judge me. So as you already asked about, the first thing that I'd like to show you guys is where is Florianópolis in Brazil. So Brazil is pretty huge. I think you guys are aware of that. So that red line is the equator line. And Florianópolis is way back down here. I'd like to keep UK here for scale. Florianópolis is actually an island. It's a pretty big city, not that big city for Brazilian standard, but like 400,000 people. We are talking a city that has been growing up really fast recently, most powered by the development of numerous tech companies. But why those tech companies are there? It's because we have 42 beautiful beaches there. It's a pretty amazing city. So if you ever go to Brazil, I strongly recommend going to Florianópolis. It's kind of out of the radar, but I would say, honestly, way better than Rio, way safer. And it's a pretty amazing city. So we have pretty beautiful beaches, but we also have these contracts with the big cities close by. So it's pretty amazing. If you ever come to Brazil, please feel free to contact me. I will be really glad to give you guys a tour around. So first of all, motivation for this talk, I just want to introduce a little bit the problem. I don't know how close you guys are here to Manchester Airport. This is easy because we're really close to Birmingham International. And it's easy to say to people, okay, so I think you believe that aircraft noise is a big problem, especially to the communities and everyone living close by to that. And it's already known for a while that the aircraft noise, especially airport noise, that what we refer to the external noise emitted by their plane, that can cause several problems to the community nearby, even, for example, children, learning deficit in children, insomnia, and even increased incidence of hypertension for those people that live close by those problems. So that's why there's so much interest in the aircraft industry in treating the aircraft noise, and it's even an important parameter in aircraft regulations. So when we talk about aircraft noise sources, we have two key sources. The red one, the ones that are written red, is what we call the airframe noise. That's every noise generated by the interactions between the flow going through the solid parts of the airplane. So we can break that into landing gear noise, which is really important during takeoff and landing. But you also have the noise generated by the turbulent flow passing through the wings, the flaps, the flats, the winglet. But the one that we're more interested in here in this talk is the turbofan engine. That's the second source that I'm going to mention. That's also going to be divided into the fan, the turbine, the compressor, and the jet. That's the one that I'm more interested in because during takeoff and landing, so the more important moments during aircraft operation in airports, the fan noise is one of the more main contributors to the overall external noise, and one of the most annoying. Therefore, one of the more penalized of these noise sources. Why it's more annoying? Because of its acoustic signature, which is given by a profusion of tones There are some to broadband noise. Tone noise, I don't know if anyone is familiar with, but it's pretty much what we can describe as a pure frequency. And for those that were not familiar what a pure frequency sounds like, it's just a whistle. So it's really annoying and really penalized during the certification process. So we need to treat that so our aircrafts can fly. And how we do it? So we use what we call acoustic liners. So first of all, I'm going to show you guys a cut view from the on typical turbofan engine, where we can see here's our fan that's actually generating the thrust, the turbine that's driving our fan. And what we actually have on that fan is a duct. So on the duct walls, we can use that space to apply some acoustic treatment. That's what we usually use, is what we call acoustic liners that we use to cover all the interior walls of our duct. And what is an acoustic liner? So the most simple construction that we have for an acoustic liner is this one that I'm showing here on the right for me, left for you guys. So we usually have a honeycomb array where we have a rigid backplate and our face sheet, preferred face sheet, that actually mimics an array of Helmholtz resonators, which are pretty much a really simple acoustic structure that we can model as a single degree of freedom mechanics. So we can model the air in the necks or in the perfect sheet as a mass, and then we can model the volume as a cavity that is compressed by this mass moving with the acoustics. So we pretty much can model that as a spring, which is going to give us a pretty nice resonance, where we're going to have a pretty peak on the attenuation. So what we want to do is we want to match the acoustic liner resonance with the band passing frequencies, was where we have the tones from our fan noise. So the problem begins with the fact that usually the turbofan engine is something huge. We are talking about something like in the narrow of 4-meter diameters for a bigger craft, like a Boeing 777, something like that. While the holes in the perforated sheet, they have diameters of around 1 millimeter. So explicitly modeling that is, I would say, impossible right now for the computational power that we have. So what we usually do is replace our acoustic liner by a boundary condition in our numerical or analytical models of a turbofan engine noise. What we usually choose is what we call the acoustic impedance. That is pretty much a relation between the force and motion. So it's the ratio of pressure and acoustic normal velocity. And is usually a complex number where we have the resistance, that's the real component that gave us a measurement of the acoustic dissipation going on the perforated face sheet, and the reactance that is usually related to the inertia phenomena going on the cavity. So this is a typical curve of acoustic liner impedances. So we pretty much have a constant resistance in the frequency range that we are interested in, and the reactance is going to have this cotangent-like behavior. So given the introduction, I'm going to talk a little bit about fundamental of duct acoustics. So since the audience is pretty much familiar with acoustics, I think you guys are going to may think this part a little bit boring. So I don't know how much of you is familiar with aeroacoustics. So I'm going to still keep this part on the presentation, right? So we need a set of equations to solve the acoustic perturbations field inside our duct. We are going to start with the equations that fluid dynamics guys gave us. So we either start with Navier-Stokes or Euler. Usually in acoustic, we're going to neglect viscosity, so we're going to use Euler equations. Then we have continuity equation, so mass conservation. We also have thermodynamic, from thermodynamics, the ideal gas equation, so equation of state, and first law of thermodynamics. This gave us 6 equations, so we can solve for the 3 components of velocity, we can solve for entropy, we can solve for pressure, and we can solve for density. So we have 6 equations, 6 variables. But the first thing in acoustics is usually the acoustic field itself are really small perturbations over some mean flow, or in this case, some time station. If we don't have flow, it's just like the ambient pressure, right? So we want to linearize these equations. So we are going to write our pressure, our density, and our velocity field as some mean flow components plus some small perturbations that is time dependent. And why we can do that? Just so I think since not everyone is used to acoustic, so just to give an order of magnitude why we can do that is because atmospheric pressure is something in the order of 10 to the 5 Pascal, not kilopascal, sorry, this is a typo. For example, in this conversation here, the acoustic pressure fluctuations that my voice is generating is maybe a little bit higher than that, but we are talking about something in the order of micropascals, so 10 to the -8 when I look to the ratio. If I go to a rock concert where something is really noisy, so we're talking about something in the order of 100 dB maybe, we're still talking about something in the ratio of 10 to the -4 in the order of magnitude, even a threshold of pain that may cause you at least severe damage to your eardrums or even instantaneous death, we're talking about something 10 to the -3. So we can linearize those equations. Long story short, when I apply when I couple the linearized formulation for the acoustic variables with the equations that I showed on the slide before, and rearrange a little bit stuff and take just the equations for the components of the acoustic perturbations, usually what we are going to end up with the linearized Euler equations. We still have 5 equations, we still have 5 variables because we still have pressure, density, and acoustic velocity components. But what we can do is simplify this a little bit more so it's more convenient to work for duct acoustics. So first thing that we're going to do is say, okay, we can assume that this dependence on time domain is something that's going to be harmonic. So let's Fourier transform that. Also, since we're talking about a duct and we kind of know that the flow is going to be moving just in the axial direction, we say, okay, let's simplify the mean flow component to a single axial parallel flow. And also we are going to say, okay, so let's skip a little bit the fact that we're going to have the flow changing inside the duct, and also that we may have some transition effects on the acoustic field. And let's assume that also the flow and the acoustics is constant along the duct axis. So we can also Fourier transform in space. So we are going to have what we call the Prismo-Brauer equation. So I get those 3 equations that I showed in the slide before. I apply those simplifications, and we end up with this wave equation formulation that we call the Prismo-Brauer equation. That is going to give you how the physics is the governing physics of the acoustic propagation inside a duct with mean flow. So this is still too complex. Usually for solving this, we still don't have computational power to solve that for a turbofan engine. So what we do is say, okay, let's skip the fact that we know that we have shear flow given the non-slip boundary condition and viscosity. We are going to assume that we have uniform flow inside the duct, and this simplify a lot our equation. And what we end up having then is just the convected Helmholtz equation. So typical, the classical wave formulation, the only thing is that we have the convection term here still coupled on the solution. Skip this. So we need to solve that equation, and we know that we have time and harmonics dependent solutions because we already included that in our hypothesis before. And we know that's going to be something that looks like a model. We're going to have a model solution. It's going to be psi times some complex explanation with the time harmonic and space harmonic solutions. We just need now some boundary conditions so we can obtain what was going to be these mode shapes and how we're going to get the solutions for our specific duct, right? So the most simple boundary condition for the acoustics is having the duct is assuming that the duct wall is rigid, so there is no acoustic absorption there. And in this case, we are saying basically that there is no acoustic velocity penetrating into the wall. And when we do that, we are going to end up with an eigenvalue problem. And from this eigenvalue problem, plus the dispersive relation between the modal, the mode solutions for the space harmonics problem that we have built, we can, for example, solve if we're solving for a cylindrical duct. we know that the mode shapes are going to look something like a Bessel function for the radial dependence of the modes, plus some complex exponential on the azimuthal direction. And how these modes looks like are more or less something like that. So we're going to have several infinite modes. Some of them are going to be propagating, like this, the first four that I'm showing here. Some of them are going to be non-propagating, non-propagative, as I'm going to be showing later. So the first mode that we have is going to be with azimuthal and radial direction order 0, with what we call the plane wave. So the whole acoustic field is propagating with the same acoustic velocity towards on the axial direction. Then we can increase either the radial order, where we start to have this Bessel-like behavior on the right direction. And when we include the effect of having a azimuthal dependence, plus the fact that we have the spatial component that's also going to be varying, going to have these spinning modes propagating inside the duct. So in the end, what we have done is we have built a model basis for our acoustic field. So in the end, any acoustic field that's propagating inside a duct, we can model by a sum of those modes multiplied by a given acoustic, by a given sound amplitude. That's going to depend on your source and how you're exciting these different modes. And as I mentioned before, we are going to have infinite mode solutions, but some of those modes, they are going to have imaginary axial wave number, which means that when I couple those to the wave equation solution, we are going to have some modes that are going to be decaying exponentially fast, so are going to be non-propagative inside our duct. So the problem is when we have a soft wall, in this case, our rigid wall boundary condition is going to be effective. We need something that is able to include the fact that we're going to have some acoustic absorption in this wall. What we usually do, we usually use the impedance boundary condition, as I mentioned some slides before. So we're going to be defining the acoustic impedance pretty much as the ratio between the acoustic pressure and the normal acoustic velocity. The only problem with this definition and our problem is that we can only use this if our mean flow has zero velocity at the wall. So we have a non-slip boundary condition for our flow field, which we already assume to be non-zero when we assume that we have a uniform flow inside the duct. So when we are solving for convected Helmholtz, we cannot use the most simple acoustic impedance boundary condition definition that we have. So we need to take into account for that in our boundary condition in some sense. Why? Why that? Because when we have shared flow, that's what we actually have inside the turbofan or inside any duct with flow. I think the animation for the guys on the team is going to be not that good. Sorry for that. But we have here, I have a monopole source where I'm showing it's propagating in free field. We have no flow over it. But when I include a parallel flow to this monopole source, we start to see Doppler effect, right? So we have convection. Here, everything is still pretty fine. We just have the typical Doppler effect that we're so familiar with. So we have this change on the effective acoustic, on the frequency of the noise, given the propagation direction. However, when I have shared flow, I'm going to also have a refraction. Why I am also having refraction? Because different portions of the wavefronts are seeing different velocities. So I also have this refraction effect given the presence of the shared flow on my mean field, right? The most common assumption that we have to solve this problem of having these refraction effects on the boundary layer is what we call the Ingrid-Myers boundary condition. That's been out for already, I think, 60 years. And how they have solved this problem, they said, okay, let's say that we have a boundary layer where we have shared flow, but let's say that is infinitely thin. We have used that for 50 years, but around 15 years ago, people start to ask questions about it. So my supervisor back in Warwick, Dr. Ed Bramley, during his PhD, he found out that this boundary condition is ill-posed in time domain. So it's already a problem when we try to get back to the time domain instead of working on frequency domain. Also, in the frequency domain, we have some problems. We're going to find some unstable modes depending on your frequency and your duct geometry, which is also a problem even for our most simple formulations in the frequency domain. But what have maybe raise more questions is the fact that poor description / prediction of the acoustic field was noticed when we were looking for waves propagating in different directions. So if problems were found in experiments that I'm going to talking a little bit later. So people will start to ask a lot of questions about if this boundary condition is the right one or not. But for the moment, let's assume that this one is correct, just so I can talk a little bit more what's going to happen with our modes when I have this absorptive boundary condition. So when I have an absorptive wall, I have an impedance boundary condition at my wall, my eigenvalue problem is going to look a little bit different. And the thing is, my wave numbers are not longer going to be either just real or imaginary. They are going to be complex. And the ratio between the real and imaginary components is going to give us an idea of how much propagative this mode is. I know this nomenclature may sound strange, but that's how we call them. So as close my mode is to the real axis, I know that this mode is usually going to be carrying a lot of energy, but now I know that all my modes are going to be carrying a little bit of energy, and my modes are going to be spread along the complex plane. So if my wave numbers are complex, this means that my modes are going to be attenuated. In this case, I have modes that are propagates outside the plane, so they're going to propagate from right to the left. So I have a lot of acoustic energy on the intake of my duct, but while my mode is propagating inside this duct with lined walls, the acoustic energy is going to be absorbed and dissipated by our acoustic treatment. So just a quick slide on impedance optimization. So the thing is, so I know that the acoustic field propagating inside the duct can be modeled by a sum of modes, and those modes are going to have some complex wave numbers. What I want to do if I want to optimize the acoustic attenuation, I pretty much want to optimize the imaginary component of the actual wave number. So we know that the transmission loss in the end is going to be pretty much given by your imaginary component of your wave number. And your wave number is going to be a function of your duct geometry, the flow field inside of it, but most important that the only parameter that we can control by the impedance. So when I want to optimize the acoustic impedance, that's going to be to maximize my acoustic attenuation. What I want to do is to find the impedance that's going to be giving me the highest component of the imaginary wave number. So the most simple way to do that is what we call the Kramer's impedance. Let's say that our duct, our nacelle of our turbofan is infinite. We have uniform flow, we have ingramized boundary condition. And for that, we have a explicit solution that we call the Kramer's impedance, which is a pretty good estimation. But we know that's not going to be working for real geometries when we have discontinuities on the line, on the ducted line. And also we're going to have the intake, the outlet that are not taken into account. So we're going to have acoustic reflections in all of those transitions, in all of those linear edges that may impact a little bit our actual optimal acoustic impedance. This picture that I'm showing here in the right is from my colleague Andreas Pilleris. He's a guy that actually worked a lot with optimal impedances. Me, I'm just actually replicating a little bit of his results. I'm not actually working on that. So as he's showing here, when he compared the actual optimal impedance that he obtained when considering all the discontinuities within the duct, the sheared flow, and the reflections at the end of the duct, with the Kramer impedance, you can see that he could get actually something like in the order of 6 dB difference on the transmission loss or a given turbofan engine nacelle. So if we know how to optimize the impedance, but how to go from the impedance to a linear geometry that I can build and put within the turbofan nacelle, right? So we go to experimental characterization of acoustic linear so we can understand for different geometries how we are going to be modeling, how we're going to be obtain different acoustic impedance. So a quick definition here that will be a little more important later. We just want to represent our acoustic linear by its frequency dependent, locally reacting acoustic impedance. What's locally reacting in this sense here? We are just saying that there is no propagation within the liner. That why we assume that? Because we have really small cavities. So we can say that the wave is just reaching the surface is going to be propagated within a linear cell and going to be reflected on the same direction, on the same point. This is important because this means that our acoustic impedance is not going to be a function of the acoustic field itself, just of the frequency. So we don't have any any dependence on the wave number and any dependence on the angle of incidence. So the linear acoustic impedance, we know is going to be a function of our geometry. Otherwise, it would be, what would be the point of having different geometries, right? So we know it's going to be frequency dependent. It's going to be depending on our cavity height. It's going to be a function also for the hole diameters and also the percentage of open area. The phase shift thickness plays a role, but it's not that relevant compared to the other three, but still something that may be important for some cases. The problem begins when we discover that this impedance is not going to be a function just of that, but also of the operational conditions. So the sun pressure level is going to affect, because we're going to have some non-linearities, because within the turbofan nacelle, we're talking about something in the narrow of 150 dB at least. But also we are going to have some effects triggered by the fact that we have mean flow here. So we expect to have some vortices going on when we have a flow passing by these holes. So they're going to be generating vortices here that are going to be changing the effective area, open area that we have here. Nowadays, we have some discussions that not also the flow velocity, but also the flow profile shape over the liner is going to be affecting the liner impedance. So the conclusion is we need experimental techniques that allow us to measure the acoustic impedance in conditions that emulates the same conditions that we would have inside the turbofan nacelle. What this means, basically, that we cannot use normal incidence tubes for those that are familiar with the acoustic impedance measurements in more traditional ways. So we need to build a facility that allows us to replicate what's inside a turbofan nacelle. How we do it? So a nacelle, as I mentioned before, is a duct. We need a duct. We need a liner sample where we can couple into a wall. We need flow, because as I mentioned before, the flow is important. We need some way to have an acoustic source that we can emulate what would be the fan. And we are going to need some microphones so we can measure this acoustic field, and from that we can actually extract the acoustic impedance, right? So this is every time that you see an acoustic lining paper, you're going to see some image like that if they're talking about something in experiments, right? So usually we have upstream and downstream sources. We have several different techniques. So this means that we have different ways to place our microphones, and from that get the acoustic impedance. The earliest technique that we have was, I would say, the more complex one in terms of instrumentation, but it's the most simple in terms of the post-processing. So the idea is to measure the impedance locally by using an in situ technique. So by using miniaturized microphones or microphone probes, the idea is to measure the acoustic pressure on the face sheet of the liner, and at the same time at the backplate of the same cavity. And from the transfer function between these two acoustic pressures, one is able to straightforwardly get the acoustic impedance. More recently, we start to work with what we call the adduction techniques that are based on the measurement of the acoustic field within the duct instead of measuring it on the sample. So for that, we spread microphones all over our duct, usually why they have them upstream or downstream through the liner sample, and usually from that we use some inverse technique. So we say, okay, let's solve the acoustic field inside the duct by using the solution for the convected Helmholtz equation that we know before, and some mode matching technique to get the acoustic field for the whole duct, and we iterate over the impedance up to we find an acoustic field that matches pretty well the experimental one. The other techniques that we use are based on Prony-like methods. I don't know if anyone's familiar. So the idea is to spread microphones on the wall opposite to the liner section. And the idea is from the pressure measurements that from equally spaced microphones there, one is able to extract directly the wave number from those algorithms. And if I have the wave number, it's straightforward to calculate the acoustic impedance that would give you this that measure wave number. So just some pictures about the in-situ technique. As I mentioned before, is the earlier technique that we have. The key problem is the instrumentation is really, how can I say, tricky. The results are not really good in terms of repeatability. Some people would say that's more kind of an art than actually experimental technique, and I would say I would agree with that. So these microphones that I'm showing here, they're like 1.6 millimeters diameter. So you will put it there, you measure, you take it off, you put it again, you get completely different results. So nobody wants to use them. That's why we all jumped into the impedance reductions boat. So about our facilities. So going to make a little bit, try to sell our liner test rig. So this is our group working with liners right now. I think actually right now there is one more guy. I still haven't met him, so it's me. That's Nicholas, who is just finishing his master right now. Professor Julio Cordioli, my supervisor back in Brazil, and the other Lucas was the guy working more on the numerics. So our test rig is actually built in an anechoic chamber, even though it's not necessary. We do this because we actually share, as I'm going to show this later, why this is in an anechoic chamber. So we have a rectangular cross-sectional duct with 40 by 100 millimeters, which is pretty decent, I would say. But the more interesting part about our facility that we can actually reach some really severe conditions. We can go up to 150 dB within the test rig in both the propagation directions. So we have both upstream and downstream acoustic sources, and we can use our compressed air system to go with Mach numbers up to 0.6 book Mach numbers or centerline 0.7. So I'm going to break down a little bit how our test facility works. So we have a flow supply system that we shared with a jet noise test rig. That's why we are inside that anechoic chamber, right? Because for the jet noise test rig, we need to be within an anechoic facility so we can measure the source. We have 100 horsepower rotary screw compressor that fills a reservoir, and from that reservoir, we have a flow control system based on a piezo tube on the inlet that gives us the desired book Mach number based on a pre-calibrated factor. So on both ends, we're going to have some anechoic termination, so we avoid to have reflections on the duct end, which is going to simplify a lot the formulations that we need to apply to solve for the induction techniques. We have 4 compression drivers on each side. That's going to give us the 150 dB that I already mentioned. And for the acoustic characterization of acoustic liners, since I am interested in the impedance for period tones, I need to use stepped sign period tones as an excitation. So what I'm saying here is pretty much the explanation why we are the most hated research group in the university. This is really annoying. We are talking about something that is annoying people really far away. 500 to 3 kilohertz, the typical frequency range that we're interested in. So 500 people are not that worried. When we start to make 3 kilohertz, a lot of people are not 3,000 kilohertz, just to make clear, 3 kilohertz. People start to show nearby, say, okay, what's the problem? Why we have this wisdom annoying everyone? I don't know if I say something on fire or not, but it's just us testing. So for the acoustic pressure, we have microphone spread, 24 flush-mounted microphone spread all over the duct from which we can get the acoustic pressure. Then we have 2 different length size. We can either measure flat liner samples to 220 millimeters or 420 millimeters, which is pretty decent. Then let me talk about what's the problem. Why we have acoustic source both upstream and downstream. Back in the day, people just used to have upstream acoustic source because it was a little bit easier to configure that. And since we are assuming that the line has an acoustic, locally reactive acoustic impedance, it was supposed to not depend on that. But on 2011, Yvan Regan from University of Le Mans, I don't know if you guys from acoustics maybe have ever heard about the university. It's a pretty big acoustic department as well. He said, okay, why not put an acoustic source on both sides and measure to see if we actually have a match between the impedances get from both directions, and he saw that no. So in blue is the typical results that we get when we have an acoustic source downstream to the liner sample. in green is what we usually get from having an acoustic source downstream to the liner sample. So we also always have this kind of trend. So we have usually the resistance for the upstream source higher than the downstream source, and say, okay, so we have this in our facility. Apparently, everyone that tried to has done that also has observed that. So what's the problem? Is that a failure of the Ingrid-Myers boundary condition? That was the first thing that he blamed on. Is that a failure of our experimental techniques? Are we doing something really wrong while measuring and everyone is doing the same mistake, which would be really strange? Are there some non-predicted fluid dynamics acoustic interactions? So, which means, is our line actually locally reactive? Or by the fact that we have these vortices going on the hole, something like that, we actually may expect to have some dependence on the acoustic propagation direction. Is impedance enough to represent a line in the wall? Some people have been discussing that to say, okay, we have the impedance at the wall, but we may need to include something else to actually model the fact that we have acoustic propagation within an absorptive surface near the wall, absorptive surface over a shared flow in a duct. And from that and so on, a lot of people have tried to include extra phenomena on the boundary conditions. So for example, some people have said, okay, the problem is that Myers has said that the boundary layer is infinitely thin. That's what my supervisor has done in the past. And also a little bit later, he has another student working on this. Say, okay, let's say that the boundary condition is not infinitely thin. The boundary condition, oh, sorry, the boundary layer is not infinitely thin, but has some finite length. That's what we call the Bromley boundary condition. Later came as in Bromley. Also, some people say, okay, the problem is, even though we are not considering the viscosity within the acoustic propagation, we may need to take into account the viscous effects within the boundary layer. That has done also by Camden and Bramley in 2017, but also by O'Hagan, the guy that had came up with the idea of measuring with both acoustic propagation directions. And other people have said, okay, the problem is we are missing the fact that we have some transfer of axial momentum between the fluid and the liner. And the thing with all of those different boundary conditions is that all of them requires an extra parameter on top of acoustic impedance to actually model the acoustic propagation within a duct with grazing flow. The problem was people were starting to develop these boundary conditions, and experimentally we had a problem. We usually have just one liner sample in our facilities, and from that, given our duct geometries and the typical frequency range that we're interested in, we usually only have one mode propagating within our duct. This means that for this whole task, we usually just had one wave number measured. So we just have two variables, the real and imaginary component from the wave number that would only allow us to get the two variables, the real and imaginary component from the impedance. And everyone was measuring everything and say, okay, so we measured it and we are not able to actually obtain the two parameters, how we can do. Some people have said, okay, so now we have solved the upstream and downstream problem. We can simply use the upstream propagating modes and the downstream propagating modes. And from these two numbers, I can get one impedance and these parameters that I'm trying to obtain. The problem is this right? And then in 2019, Bramley, my supervisor here, met with Julio, my supervisor in Brazil, and they met in a conference in the US. And Matt said, okay, Julio, I think I have an idea on how we can test this with just upstream or downstream propagating modes. And his idea was pretty smart. He said, okay, if I have one lined wall, I have one wave number. If I have an identical liner sample to put on the other wall, I'm going to have another wave number for the same propagation direction for the same liner. So with that, I can test all of those boundary conditions and see if the acoustic field that I'm getting for these two different conditions with just one liner or two liners, they match. We have tried that in terms of looking for the scattering matrix. So we are basically looking for the transmission loss and the reflection coefficients at the lined edges. And what we observed is actually none of those boundary conditions are able to predict exactly, especially the reflection coefficients that we were obtaining experimentally. So the conclusion was, okay, so we have a lot of different boundary conditions, but we still don't know exactly which one of those is the best one to represent the acoustic field within a lined duct. So I'm going to jump a little bit for what people have been doing more recently. And that's what I'm working right now with Ed. The thing is, what the problem is the uniform flow hypothesis. What if the problem is all on the fact that we are solving convected Helmholtz with uniform flow and trying to take into account for everything into a boundary condition, while the problem is just in the modes, not just on the boundary condition. Some people have been working on that in the past. Some guys from on the French Aerospace Research Center on EHA have solved the impedance reduction using linearized Euler equation. My colleague also have worked by solving explicitly Pridmore-Brown. What they have found is that something apparently is there. The results that they obtain suggest that the curves between upstream and downstream are getting to a collapse, but still looks that there's something wrong. And what I'm working right now is how to include the shared flow in those set of equations. With that said, with the problem of linears, the key thing is, okay, so we were talking about something that we have been using for 60 years. Apparently there's a problem with the modeling, but airplanes still fly. They're still getting certificated. So why we're still looking to linears and why we're still trying to solve this problem? And the key thing is what the future is keeping for us and what we may need to worry about it. So right now, talking about traditional aircraft, we have this trend of the increasing bypass ratio. So we know for a while that by increasing the amount of air that pass through the engine, not by the turbine, but by outside, powered by the fan, increases the air fuel performance and also reduces the noise. But why we have been building this guy so big since the early days is the fact that the rotational speed of the turbine is usually constant and really high. And if we want to have a really big fan, having this really high velocity is going to be a big trouble. So we need to build some efficient and reliable gearboxes so we can have different velocities between the turbine and the fan. And that's something that we are accomplishing right now. So that's why, as you can see, the new Boeing 737 MAX, the 320 Neo, the fact is they are just getting bigger engines that are more fuel efficient. And what this means for acoustics? So what this means is the fact that if we increase the fan, we usually reduce the speed, which means that we are reducing the blading passing frequency, which means that we are reducing the fundamental frequency that we want to treat with the liner. This means that we usually need to have like bigger liners, but we don't have this space within the nacelle. So we may need to develop new type of lines that may be able to actually treat to attenuate lower frequencies. And that's why we're still having interest in working for acoustic liners for turbofan engines. But and also that, if you go to, Deepak was last week on the IAA. If you go to our acoustics conference right now, you're going to see a shift. Half of the acoustics community is working with propellers. One, because traditional aircraft is going through an electrification procedure, and for electric motors, it's usually better to work with distributed propellers instead of working with a turbofan. And also, we are seeing a lot of propellers being applied for these new air vehicles that we have been seeing a lot. So flying cars, or eVTOLs, as someone would say. And the thing is, propeller is going to be pretty much noisy and the same type of acoustic signature that we would expect for a turbofan engine. So they're going to be a problem as well, and why we don't try to use liners to solve the same problem that we have solved for the turbofan engines in the past. The key problem is, if you look for the typical design, usually there is no duct on the propeller. So first thing you need to do is to convince the aircraft industry to use something like this one, that we actually have some shrouded propeller, so we have some space to treat. And the other problem is the same one that we have for ultra high bypass ratio. Usually the blade counting is really low and the RPM is really low, which means that the typical tone frequency for propellers is really small. So it would be really challenging to use traditional liner concepts for this type of application. So that's the current trend right now. People are trying to develop liners for a more broadband range, for lower frequencies. And that's why we're still interested in. But the problem is, if we don't understand exactly what's going on the acoustic propagation, how can we be sure that these new impedances that we are be targeting are going to be working the best? With that, I would like to thank you all for your attention, and also our current sponsor on the acoustic liner research that we have in the lab. It's the Acoustics Research Consortium in Ohio. Some part of these presentations were supposed, actually I removed them, but we have this collaboration going on with the guys from NASA Langley Research Center and Professor Francesco Avaloni from Politecnico di Torino. And for that, I would be keen to try to answer some questions. Thank you very much for your attention.
Do we have any questions in the room? John?
Hiya, thanks for a nice talk. One of the things I've kind of heard about is that you obviously design these liners to absorb some frequency, but particularly in kind of electric driven things such as drones and stuff, the blade pass frequency is not constant. They change. Are there any strategies for
Broadband line.
Yeah. Just broadband.
Yeah, if I had somewhere that I can draw, like what people is doing is how to get a broadband liner. Usually what they're doing is either having a metamaterial or having, for example, varying liner depth, cavity depth. So you would have different cavities with different resonances, would give you a more broad attenuation range.
Oh. Are you playing with fire?
Playing with fire. Press the button on the screen. And
Maybe I need to change for the.
no,
Oh, you're in the laptop.
If we press,
It's all right. I get the idea. It's all right.
that'd be cool to do.
Okay. Right. So imagine that you would have like. Imagine that the black line is a preferred sheet, right? I'm not going to draw all the rows because otherwise I'm going to. And you have your cavities here. And then you have your rigid backplate. So usually you have this constant cavity depth. What people have been working is either having some variable cavity height, or also what people have been trying to do is to have more fancy structure. So like imagine that one cavity is not going to be just holes here. Let me do that. Instead of having one hole within a cavity in the backplate here, what people are working is one is having different cavity structures. For example, having one hole here, but your cavity actually does something like this. So your effective cavity length is this thing here. So by playing around with this kind of construction, you can have different cavity lengths for different portions of the liner, so you can reach different liner resonances within the same sample.
That's reminded me actually of a paper from Dyson actually, which was quite interesting. I'll just tell you this because it's related, where they actually looked at having Helmholtz resonators that had quite a long thin cavity instead of the classic fairly sort of straight portions, and the hole was kind of in the end of it. And what happened was the cavity actually had modes, so you didn't just get the one sort of base absorption frequency, you got several absorption frequencies at the different modes of this thing, and they were tuning trying to resolve harmonics.
Another solution, for example, more simple, this one is already really used, is what we call the double debrief liner. That is, you have the preferred phase sheet, then you have the cavity, and then you use some septum, some really thin mesh that kind of creates two virtual cavities here. So you're going to have this resonance, and the whole thing resonance. So you can have like 3 peaks, and this increases a lot the broadband attenuation. The key thing for like the drones and eVTOL stuff is convincing people that it's worth putting more weight and giving up a little bit of aerodynamic performance for noise treatment. I think this is going to be a question more in the next years because right now they are building prototypes and flying within confined environments. I believe when they start to fly around cities, they're going to say, okay, we need to solve the noise. But right now, not so many companies are actually working strong on that. That's at least the impression that I got from the IAA. I don't know you, Deepak. How?
Thanks.
Thanks for a great presentation. You had a slide where you were talking about researchers looking at a bit more what was going on. I think you mentioned Bramley and Oregon. Are you able to explain the difference between what those different papers were focusing on?
You
Maybe
say
just give a bit more.
this one?
Yeah. What is there a difference between what these were?
Okay, so the first bullet point, so Bramley and Camis Bramley, the thing was just saying, okay, the boundary layer is not infinitely thin. That's what Ingrid Myers assumed when they derived their boundary conditions. They said, okay, there is some thickness on the shared flow component within the depth. Then those guys on the middle bullet point, they said, okay, the problem is viscosity. Because since the beginning, when we start to derive the equations, we dropped viscosity, because this is really true for acoustic propagation. The problem is they're saying, okay, we need to take into account for viscosity at least within the thin boundary layer, because there is a region that for the flow, it's really important, the viscosity there, so it may be important to us for the acoustic propagation, so we may have some dissipation going on there. And this may be different if your wave is propagating with or against the flow. And the second thing, this one is a little bit more tricky to explain, and I'm may gonna try to dry, but this may be a problem. Let me just find a slide if I have a lot of white space. This one, okay. So imagine that, again, the green line here is your lined wall. You have a shared flow here, right? What these people are saying is, since I have acoustic propagation here, so I have some momentum on the wall, and I have this shared flow over the lined wall, I'm going to have some transfer of momentum between the acoustics and the shared flow. That's not taken into account when I just say that, okay, my wall is represented by an impedance. So that's something that may be included as external factor. They usually represent that as a shear stress, something like that. And those are the three schools going on right now. So the first one was just saying, okay, the problem is finite boundary layer, then saying, okay, you have viscosity, and those people are saying, okay, it's just a balance of momentum problem. Sorry. Thanks very much.
Any other question?
Yeah.
So my colleague John asked you about the drones basically changing RPM quite rapidly, and you suggested the broadband, so align it to with a broadband response. So have you worked or have you thought about these liners when you have different flying stages, so takeoff, landing, so this noise signature is going to change significantly. So have you thought on those?
So yeah, so like that's a really good question, and my answer is no. Like I would say that, like, for example, for traditional aircraft, for cabin noise, the fan is not a big problem. It's more for like the airport region. So there we just need to care about takeoff and landing and approaching. So like the line is tuned for this. This is usually like full throttle, right? So we tune the line for that situation. For the eVTOL, yeah, the thing would be we would take into account in some sense for the different stages of flight that may be varying a lot during and all the time that their vehicle is going to be close to the community. And in that case, yes, you're definitely going to be needing to need a broadband liner or some different source of control. So you would keep your propeller rotating in constant speed and use different mechanisms to vary your throttle, the thrust, you know, varying the pitch, something like that could be an option. I don't know if it's like feasible, but yeah, I think those are the two options that I could see, like or either a broadband liner or a way to keep the RPM constant
Oh.
and changing thrust. in
We'll
the
see.
segment.
Thank you for your presentation. Really good work.
Thanks.
I have one final question if no one has. You said that you are trying to reach to a sound pressure level of 150 dB in your experimental test setup. So definitely you will have a nonlinear effects into your liner. So like which part is getting most affected is like resistance or have you saw any effect on reactance as such?
Change a little bit,
Yeah.
but it's mostly on the resistance that you have increasing resistance. But to be really honest, when you have flow, everything above Mach 0.2, the effect of the sound pressure level is almost negligible compared to the flow effect.
Flow effects. Okay.
Just really close to the resonance that you may have some small peak on the resistance, but usually when you have flow, the flow is going to dominate and it's going to be way higher component than the.
Yeah. And another one thing which I was a bit more interested is like when you see the resistance is increasing with the sound pressure level.
Yeah.
At some point, does it like gives a kind of you may get a higher resistance and will it try to act as a kind of hard wall?
It will need to be a really, really, really high sound pressure level to go to that point. Yeah, but the thing is, if you increase the resistance, if you go increasing at some point, it becomes hard wall.
Thanks.
Yes.
Any other questions? No, right? Okay. Thanks, Lucas. Then thank you very much for a nice talk.